Hello, in this screencast we are going to introduce the central limit theorem. Let's consider an experiment which consists of flipping multiple coins, adding up the numbers corresponding to faces and dividing it by the number of coins. In other words, the output of the experiment is the average of the coin flips where we substitute numbers instead of coin faces, 1 for tails and 0 for heads. If we flip n such coins, the sample space consists of integer multiples of 1 over n, starting from 0 up to 1. In other words, we can observe as the outcome of the experiment any I over n where 0 less than or equal to I less than or equal to n. We know that getting a 0 or a 1 from an individual coin flip has equal probability, 0.5. What happens as we increase the number of coins n? What is the probability density function, in this particular discrete example a probability mass function, for the outcomes in our sample space? Let's start our investigation from n equal to 2, where we have three outcomes: 0, 0.5 and 1. 0 corresponds to getting 2 heads, 1 corresponds to getting 2 tails, and 0.5 corresponds to getting a tail and a head, or head and a tail. Thus, probability of the outcome 1 over 2 is equal to 1 over 2, and the outcomes 0 and 1 have both 1 over 4 probability. For n is equal to 3, we have 4 outcomes: 0, 1 over 3, 2 over 3, and 1. This time we have 1 over 8, 3 over 8, 3 over 8 again, and 1 over 8 for probabilities of the outcomes. And we can keep increasing the number. If we keep increasing the number of coins involved in the experiment and plot histograms after many trials, we observe a trend in how the histogram changes with increasing number of coins. The histogram starts resembling a bell shape. More specifically, the histogram appears to coincide with the Gaussian density function. Central limit theorem tells us that this is no mere accident. Central limit theorem tells us that if a random variable consists of the average of n independent random variables with identical distributions, finite mean mu and variance sigma squared of course, the probability density function of that random variable converges to Gaussian PDF with mean mu and variance sigma squared over n. Let's see how this formal definition is applied to practical applications. In statistics, it's very common that the distribution of the collected data is modeled quite accurately with a Gaussian distribution. Consider, for example, the height distribution from a medical study. There are many factors contributing to the height of a person, such as genetics, nutrition, physical activity, climate. All these effects, in a sense, add up in the measure of a person's height. Whenever the measured quantity is due to small contributions from a variety of factors, Gaussian distribution is usually a good fit for the collected data. Fitting the Gaussian distribution to the collected data is also quite useful when evaluating the statistics. While the formulation of the density function looks complicated, the Gaussian distribution is actually quite simple and intuitive. The mean and the variance uniquely determine the Gaussian distribution. They are the only two controlling parameters in the density function. These parameters themselves are quite intuitive. The average of the data gives an indication of the quantities we are dealing with, and being above or below the average is already a meaningful information. Moreover, assessment of how far a particular measurement is from the average is also easy once the difference between a measurement and the average is normalized by the standard deviation. Or, in other words, we can assess how probable it is to have a measurement that's at a certain distance from the mean based on the Gaussian distribution. So this is the end of the screencast introducing the central limit theorem. Thank you for your attention.